energy equation. In other words, we look at the energy at some initial point and we look at the energy at some final point and we equate the two. So sort of a balancing of accounts. Or we can look at the same equation, but in terms of changes in the account. So any change in account one plus a change in account two will equal to the overall change in accounts. In other words, the transfer from one account to another. So the two methods, let's say, um, we are going to start with the example in our notes, example 1464. The method that is given in that example. So in your handout, you should have the answer already there for you in detail using method number 2. So we're going to do the same problem using method number 1 instead, since you already have method number 2 in the notes. So I'm going to start sharing screen in just a second. I'm just going to set up a file here to work with. Okay. Copy the problem here. Okay, all's good. So here we go. Okay, so this is our problem. We are told that mass A and B are fastened together by a belt over pulley D. We're assuming that there's no slipping of the belt. So everything is in good contact. We're told the mass moment of inertia of the pulley is 15 kilograms meter squared. We're told initially that the system is at rest and then released from rest. Once it's released from rest, we're asked to find how far does mass B drop before reaching a velocity of 2 meters per second. So mass B is falling. When it reaches a velocity of 2 meters per second, how far has it dropped? So what do we do in this case? What is the first thing that we set up? Well, it's an energy approach in this case. So we are going to use method 1, conservation of energy. Actually, I'm just going to move this over because I want to have more space. Okay. So we're going to use method 1. I should say conservation of energy method 1 because they're both conservation of energy methods. So in this case, we're going to see now that we have 3 objects So things get a little bit long and complicated. We have objects A, B, and D. So in general, our equation in general has this form. Kinetic energy initial plus gravitational potential energy initial, if we have spring potential energy initial, plus any work done by any applied force that is not gravitational or the spring force as the object moves from initial to final position, equals the K final, UG final, U spring final. Now, in this case, we have three objects. So we're going to have three kinetic energies, three gravitational potential energies. We have no springs, so this does not play a role. We're not told that, oh, actually, we are told there is friction. So we have friction here. We have to take into account. And we're told that the whole system starts from rest. So K initial is going to be 0 for all of them. But in general, we don't have the spring potential energy. And so we have this. We now have to set up the kinetic energy for all three objects. So kinetic energy initial, A, B, and D. So kinetic energy of A initial plus kinetic energy of B initial plus kinetic energy of D initial plus the gravitational potential energy of A initial plus the gravitational potential energy of B initial plus the gravitational potential energy of D initial plus the work done by friction as the object moves from I to F, from initial to final position. So which object actually experiences friction is object A. So as object A moves from initial to final position. Now we're going to look at our kinetic energy of block A final plus kinetic energy of block B final plus kinetic energy of block D final plus gravitational potential energy of A final, gravitational potential energy of B final plus gravitational potential energy of D final. Now we said that the system starts from rest, so these are all 0. Next, this is where this method is not as convenient as method 2. Why? Because in this particular case, we have to set a 0 reference for the gravitational potential energies in order for us to be able to solve them. And the 0 reference doesn't have to be the same for each object. So that's where, again, it becomes a little bit more complicated. Now, gravitational potential energy of block A. So this is our block A. It starts here, and then it ends up somewhere, let's say here. B starts here, and then it ends up somewhere down here. So now, we need to call some point, some height, the 0 reference for block A. So you can call the initial position of block A the 0 reference for block A. So we could call this our 0 reference. Similarly, we can call the initial position of block B the 0 reference. And now, when it comes to the pulley, we could even call the initial position of the pulley the 0 reference for the pulley. Any questions so far?
Could you go over why they're considered 0 reference and why they have no value? This is for Ki and UGI, yes?
Not for Ki, only for UGI. The Ks are 0 because they start from rest.
Okay, perfect. And
the U's are 0 because to measure a potential energy, you always need a reference height.
Okay,
Your
so
0 height. So we're calling their initial heights their 0 reference heights.
Okay, so in all technicality, when we have a problem like this,
you always have to need a 0 reference. Oh, no, it has nothing to do with starting from rest. But this has nothing to do with starting from rest.
Okay. I'm just trying to wrap my head around the potential energy.
Well, the potential energy is measured with respect to position. So you need to give a 0 reference. So for example, if you're entering an elevator and the main floor is considered the 0 floor, and then you go 2 floors up, you're 2 floors above the main floor. But if you call the basement, like 1 floor below the main floor, your 0 reference, then you're 3 floors above the basement.
Okay, so just so I understand, because there's, let's say if I just take UGAI and then UGAF, one of them is going to have to be 0 to be the 0 reference.
Not necessarily. You could always pick any point to be your 0 reference. You could even pick this point or this point to be your 0 reference. But if you want to simplify the math, it's best to pick either your initial or final position to be your 0 reference. Your 0 reference
Okay,
could
yeah,
be any
so
point, but it's just mathematically easier if you just
okay,
pick one of the points. That way you eliminate them. Because in
okay.
theory, you could have
So is
said,
that why all three of
well, no,
Oh, is it
they
because like
each need a 0
UG
reference because you need the change in height.
Okay, so like let's say UGIA could be a 0 reference, but then like let's say if UGBI isn't a 0 reference,
Then you could say
UGBF would be the 0
UGBF could
reference.
be, yeah, exactly.
Okay, but like
Yeah.
because there's like multiple of them, one
Mhm.
of them has to be a 0 reference for the other one to be potential energy because it's with relation to a height.
It's not necessarily that one of them has to be 0. Like I said, you could have this as your 0 reference for all 3 of them, for example.
It's just
And
I'm
then
asking
Mhm.
more what would be the case where like let's say if we take UGAI again
Mhm.
isn't 0, but
Mhm.
UGAF also isn't 0.
Yeah, that's what I'm saying. So if you
Like we're
choose
both
if you
okay.
choose this here to be your 0 reference for all of them, and then your
Okay.
UGAI is whatever height this is. Okay, so you use this height for UGAI. Then you can
Oh.
use this height for
Oh.
UGDI, or you can use this height. And then when you're doing the final and B is down here, you're going to measure this with respect to this height. Then this one doesn't
Oh,
change. And then
okay.
you can always, when A is over here, you can measure its height from its 0 reference here. So the 0 reference could be the same for all 3, different
Okay.
for all
It's just
3.
having it in the initial position is just it makes life a lot easier because it would be the height of let's say B, it goes down. And since that's what we're looking for, it gives you the
Actually,
answer straight up.
yes, exactly. And I'm just going to share screen here for a second. This method, which uses the change in height, you don't have to worry about the 0 reference per se because you're looking at what is the actual change in height. So it eliminates the need for determining a 0 reference
Okay.
because the 0 reference would cancel out. So that's why it's not important that what your 0 reference is that you need it just so that you can have some idea of what the change in height is
Okay.
if you use this
And
method.
so just one last
Mhm.
okay. So just one last question with relation to this problem. If we could just go back,
Mhm.
just so I could see the problem fully. Sorry.
Mhm.
Just to make sure that I fully understand, because this is something I do want to understand. With the way we're going about it at this moment, when the A changes, we're
Mhm.
taking the A between where it's currently and then its final position in height. Yes.
That's right. Yeah. It has to
Just
be
to
height
clarify.
because
Okay,
that's the
perfect. For
definition for
D,
gravitational. Yeah.
okay, and for D, it's going to be with relation to rotational
No,
displacement rather than.
gravitational. No. Gravitational is just height. The definition of gravitational is mgh.
Yeah, it's more because since it doesn't actually move, would there be something in the formula like it doesn't go up or
No. But
down,
I'm
it's
saying,
spin.
you just apply the formula. So we'll get there in just a second. And then you
Okay,
can ask me
perfect.
again. Okay.
Okay, perfect. Thank you.
No problem. So we chose their initial positions to be their 0 references. And work done by friction now is not going to be 0 because we do have friction present. So far, these are the simplifications that we can make. There is one more simplification, but we'll go through it in just a sec. So 0 reference is done. Objects at rest, so initial kinetic energies are 0. The rest we have to evaluate. Work done by friction. The formula is always minus Fk, the distance traveled by the thing that is experiencing friction. So the distance from initial to final position. And this is basically for block A because block A is the only one that is experiencing friction. So I'll put A here just as a reminder. Now the kinetic energy final of block A is going to have the form 1/2 ma VAF squared. The kinetic energy of block B is going to have the form 1/2 mb VBF squared. kinetic energy of the pulley, well, the pulley is rotating, so it's not a linear form. It's going to be 1/2 I omega squared. So I for the pulley, P for the pulley, but since it's been labeled D, I'll use D. So we have the kinetic energies. Now the gravitational potential energy of block A when it's at this position. This is its zero reference. This is its new height. So this is the zero height that it started off with. Now it's at this height here. What is that height with respect to this? How would you write it? Okay, think about that because we're going to be doing just that in a second. Same for block B. Block B will descend a certain height. So MBGHBF. Now, the pulley, does it change heights? What is the height of the pulley? What is the final height of the pulley?
Same as the initial.
Which is?
0.
0. So the height, the final height of the pulley is 0 because the pulley hasn't moved. It's at its initial height position, which we call the zero reference. So the final height of the pulley is 0, which means it has no gravitational potential energy and no change in gravitational potential energy because it hasn't changed height at all. So this whole thing goes to 0. Now, as we go along here, if we look at all of this, we don't know VA final. We don't know this. We do know VB final because it's 2 meters per second. We're given that value. We don't know omega D. We don't know as yet the height of block A, the final height of block A. We don't know the final height of block B. In fact, we need to find this. Now, I said that we don't know VAF and omega D. In a way, we do know VAF and omega D. We're just not given that information. So I'm actually going to do this instead. We are actually given this. Should have just put that. Now, we know the V of B when it has dropped. Do we know the V of A when it has moved to here? And if so, how do we know it?
Would it be the same velocity as the mass B dropping?
Why?
Because they're attached by tension.
Yeah.
Rope?
So remember, block B is in contact with the pulley through the rope, and block A is in contact again with the pulley at the same position, outer rim. So these points here have the same V10. So in other words, VBF is equal to VAF is going to be equal to VD of the pulley at the rim. Now, VD of the pulley at the rim is just RD omega D. Okay, so we have all that information now. So in actual fact, we know all of this. When it comes to the heights now.
Miss, can I just ask one question?
Mhm.
It's just about what you were talking about before earlier for the negative FKD.
Mhm.
Are we going to end up using the, I always forget the name of that little symbol that's next to the 0.3
Next
times
to the-
normal force?
Yeah,
So you know that I don't remember the name of that. That's
mu.
Mu,
It
okay.
looks like a U, so just call it a mu, I guess. Yeah.
Okay. So are we going to end up using the formula mu normal equals FK?
Yep.
And so the D, what does that is that the D for the
That's the distance no, it's the distance
Okay.
where we have friction. Here's where we have friction. So A moves from here to here. This is where
Okay.
we have friction. This is the only
And-
place we have friction.
And would that distance be the same amount of distance that the B ends up dropping at?
This distance here is the same as, yeah. So that's why we're going to do this over here. We're going to,
Okay, so we're finding D with A with relation to A, not D with relation to B, but they end up being the same number.
yes. So we have
Okay.
to link the remaining unknowns because there's too many unknowns. We only have one equation. So that means they're linked.
Okay, and for that formula, because I'm also using the cheat sheet you gave us, basically.
Mhm, mhm.
It's because that formula FKD, I don't think it's on here. Could
It's
we write it
written
in?
as FK, I think just delta X or something, because it's just the work formula of the force of friction times displacement cosine 180, or minus, if you choose the signs, plus or minus, because friction is always opposite the motion. So it's always
Okay, so it'd
minus
be
Fx delta X. FK delta X, I should say.
because right now what we have
Right now
here
you
is
have your,
W equals F delta S cos theta.
that's right. And
as a
cos
formula.
is 180. So cosine of 180 is always a minus sign.
Okay, and so this formula
Mhm.
is basically the FKDI, but with F we're putting in mu. Or sorry, with
we're
FK
putting
we're
mu
putting
K-
in
mu
KN.
Kn, the definition from FK, yeah.
Okay. Okay, perfect.
Okay. So these are our V's, and now our H's and the D's are all going to be related.
Miss,
Yes,
the H is with respect to what point?
the zero references that we chose.
Which one did we choose?
What did we say over here? These are set to 0. Why? Why did we set these to 0?
I don't see what you're pointing at.
Why did we set UGA initial, UGB initial, and UGD initial to 0?
I don't know.
So why did we set, let's say, KA initial and KB initial and KD initial to 0?
Because they started from rest.
Yeah, okay. And so then the UGs, why did we set them to 0?
Because height is 0.
What height is 0?
Like the reference point.
Yeah, so we chose our references. Our
Okay,
reference
so
height for each object.
okay, so the starting point will be 0 for every individual weight.
Yeah, I went over that with Ailish. You don't have to have the same reference point. They could be different, or they could be, you can have the same 0 reference point. We chose them differently.
Okay, thank you.
So all our heights are going to be measured according to the 0 references chosen in this case for each object.
Okay.
So our HAF and HBF and HDF in this case is 0. So they're all going to be measured with respect to their 0 references.
Okay, thank you.
You're welcome. So in this case, we have the V's related and we have the D's and H's related. So as B drops, so specifically we are interested in HBF. That's what we are looking for. Now the height that B drops is going to be the height HBF that it drops is equal to the distance traveled by A up the ramp. So HBF is going to equal to D initial position to final of A. So this D here, I'll put the, yes, I can put the A here. The friction acts on A. So this height here is equal to this D over here. And we know that the height difference for block A is this. So how do we find the height that block A has climbed? Not the distance up the ramp, but the height it has been raised.
We would need D, and then we'd be able to use either Pythagoras, sine law, cosine law, or tan law.
Yeah.
Well,
so
tan.
which one is the easiest one, let's say, to use? given what the information you have in the diagram? Because you're given some information in the diagram.
I would say tan
You could,
or
but
sine, just because it's easy ratios. But we would need at least one of the three sides to be able to use either of those two. So we have
okay.
to find D that you just erased for us to be able to
You
use
don't have
those.
to find it, but let's say this is the final position, this is the initial position. So A would be here finally, and this would be the final position for B. So actually, I'll do that. I'll call it AF and A. So this is AF. This is A initial. This is the distance D traveled. Oh boy. I'll do this instead. So this is the distance D traveled. And so how do you relate that to your H of A? So this is your D for A, and your H. I'm just going to bring it lower. And your H is from here to here. So how do we find that H?
Cosine law.
There's something simpler,
Python.
sort of along the Pythagoras and tan, but how? So what do? You're given information on the diagram.
Are you looking for an answer like we use one of the first laws we learned?
No. No, I'm saying that you literally have the information on the diagram.
Would you be able to use the pulley and the arc
It's simpler than that.
length?
No, it's much simpler than that.
Because I know it has something to do with the 3 and the 4, obviously.
Exactly. That's exactly it. What
It's
does it have to do with it? What is the 3 and 4
Would it
there
be something
for?
along the lines of like 3? Well, it's a ratio as to the incline of the plane.
Okay, so we
Would
are
it-
looking for the vertical side there. We are looking for this H here. HAF.
Would the answer end up being something with like an X variable in it that we'd have to solve for?
No, guys, you're overcomplicating things. You have HAF and you have DA. You have to relate those two. How are you going to relate them? DAF and HF, how are they related?
It's a similar triangle.
Okay, so what would you do? You had said you could use sine, you can use tan. Which one would you use?
You could use tan 3 over 4.
But why would you use tan 3 over 4 when you don't have the cosine side, the adjacent side, or the opposite side?
Hold on. So good. Would it be sine?
Okay.
Sine opposite over hypotenuse. So-
Okay. So,
So
what are-
sine HAF over DA.
HAF is not an angle, so you cannot say sine HAF.
Oh, sorry. Well, I mean, it's to find, oh no, that would be to find the angle.
Okay, but write it. What would you write?
Mm,
Sine of what?
3 over 4.
Okay, guys, this is why
Mm.
when I take off marks, let's say for the way you write things, it's because by having teachers who do not correct you over the years about how you write things creates these type of problems. You could only have sine of an angle, and sine of an angle is equal to opposite over hypotenuse. So sine of this angle here is opposite over hypotenuse. Opposite in this case is HAF, and hypotenuse is DA. And like you said, you have similar triangles. So sine of theta is also equal to 3 over 5. Because it's a 3, 4, 5 triangle. In which case, your HAF is going to be 3/5 DA, or DA is equal to 5/3 HAF. But really, it's best to write it as 3/5 to keep it as a sine thing. Your HAF is equal to DA sine theta. So in this case, we have this relationship, and that HAF is equal to DA sine theta. So all of our H's here have been written in terms of one variable, our DA. Now that we have our HBF and our HAF written in terms of D, this equation only has one unknown, the D. We still have the FK here to worry about. And our FK is equal to mu Kn, like Eilish had said. But our N is equal to what in this case? Because we're not given any N, but we are given some information. How do we find N?
By finding FG. No, hold on.
Okay, yeah, but in part that's true, but
F
a little
O
bit
F
more.
F FG cosine, I think,
Okay,
of
so
the
what are you?
angle.
Okay, so what is it that you're doing
So-
in doing that? Let's say.
We're basically using, I think it's the first method.
Second
Method, sorry. Where
second
you're
law,
using
second law
second law. Yeah,
of
where you
Newton.
have okay, yeah.
So,
So it's 35 times 9.81.
Yeah.
Which would be FG. And then you times that by, in this case, it would be, angles are always what confuse me.
So again, you're going to be using this 3/4 thing. So
Yeah.
this angle here is the same green angle that I indicated there. The angle of the
Okay.
slope. So whenever you have a slope, well, let me try it a little bit better. Whenever you have an incline like this and you have a block on it, the angle that FG makes with a normal is always the angle of the incline.
Okay.
So in this case, this angle here is the same one here. So N is, like you said, FG, and it's going to be adjacent. So cosine theta.
Okay.
And in this case, adjacent is going to be not 3/5, but I mean, cosine
4/5.
theta is 4/5, exactly.
4/5.
4/5. Okay, so that's going to be
Okay.
all the information that we have. So this part is not so bad, but it's this part that we have to know, because without these equations down here, this problem is not solvable. Okay, so you need to know that the V's are the same, that these H's are interrelated. They're not independent of another. Why? Because as B drops, A goes up, and the distance traveled along the incline is related to the height because of the triangle over here. Okay. So with these equations, now we substitute back into here and we solve. So I'm just going to try to squeeze everything in. I don't think I will be able to. I thought so. Oops. Why is it doing that for? Hey, let me try and get this up there. Whoa. Okay, so now let me see what other color we can use. So making our substitutions for our FK, mu KN, so mu K, mg 4/5 is equal to this side here, 1/2 mass of A. VA is like VB, so we're going to write it in terms of VB because we're looking for VB. Squared plus 1/2 MB VBF squared plus 1/2 ID. Now, omega D here is going to equal to VBF divided by RD. Does everybody see that? Okay, all we did is solve for VD. And in this case, VD, sorry, solving for omega D. And in this case, omega D is VD divided by RD, but VD is VBF. Everybody okay? Okay. Now we're going to have MAG or HAF in this case is DA sine theta. And sine theta in this case is 3/5. I didn't finish off over here. DA 3/5. Our next one here is MGHBF. Our HBF is our DA. And we don't have anything else. We pretty much took care of, oops, I forgot the D over here, guys. FKD. Just squeeze it in properly. So now in this case, the only unknown in this equation is this one thing, dA, which is what we're being asked to find. Everything else we have a number for. So let's bring all the dAs over to one side and everything that it does not have a dA to the other side so that we could isolate the dA. So we're going to keep this dA over here, minus mu k mg 4/5 dA. This dA comes over, becomes minus again, MAG dA 3/5. That one also comes over. The rest stays on the side. Now just simply simplifying things, factoring out the dA and leaving the rest of the factors there. Mu k mg 4/5. Actually, I'm going to bring the numbers out in the front. 4/5 mu k mg minus 3/5 mag minus mbg. Oh, this one was A here. Should put A here. Should put A because it's the friction on A. We factored out the dA. Now this is just one big number. We have all the values for this thing. All I'm going to do is rewrite it. I'm just going to bring in the squares. So we have this. We know everything except for dA. We have a number for everything there except for dA. Okay. So what is our next step? Plug in your numbers for everything here. What is this first bracket equal to? If you plug in your numbers, you have everything. You have the masses, you have mu k, you know what G is. Guys, plug in your numbers.
After plugging everything in,
Mhm.
if I did it correctly, I think dA should equal to negative 0.64.
Negative 0.64.
So I'm assuming that means it's going down.
In this case,
Because-
because this, sorry, go ahead.
Well, no, it's just because
It
since
should be
it's
a
neg-
positive, it should in theory give you a positive number, but it brings up a good point that we did not take into account and we should take into account. Very good point though, because there is a mistake somewhere here. And the mistake is as follows. That HBF here is equal to dA. It's actually equal to minus dA because it goes below its zero reference. HAF is positive because it's above its zero reference. So this one is indeed a plus. And the rest
Okay, so-
is, so in this particular case, that stays the same. This here, where we have just the A for HB, that should be a plus.
Oh, where did you make the changes, Miss? Could you maybe use like a pointer?
Can you see it like in like very thick plus
Okay,
here?
okay, yeah.
And a thick minus over here. And this one remains a plus. Okay, and so we have to make sure that we put in the proper signs. So this one got displaced up from its zero reference, so it stays positive. This one got displaced down from its zero reference, so it must be negative. So in this case, it was negative because we moved it over from here. Oh, I have to make the correction on here. Sorry. as well. Oops. Minus sign over here.
Well, because I was, at least in my equation, I was solving for, okay, yeah, I know, for dA.
Mhm.
So because it goes up, it's in, oh, hold on, now I'm confused. Sorry.
I'm just saying that because if we take it into account our signs correctly, your DA should be positive. It should always be positive.
Because it's going up, but because we were solving for dB,
It
'cause it's the
doesn't
same
matter.
thing.
It should still give you a positive because we put it here as a negative
Wait, where do we put it as a negative?
in the
Where the
definition
stick-
here. Here.
Oh, okay, so my answer is negative because I didn't have that in the definition.
And it's also wrong because it doesn't, this sign should be positive, so it won't give you the same answer.
Okay. Okay.
We have to
I
put
just
the
have-
negative sign from the beginning is basically what I've said. And,
Okay.
and because you got a negative sign, it reminded me that we forgot to do it because it should give you a
Okay.
positive.
Okay. Okay, perfect.
Okay. So with that change, with the positive there, we get what?
Okay, so it's still 0.64. I see where in my work now where the mistake was. It's just
Okay.
that the number attached to dA, I
Mhm.
had it both added, but they should have been subtracted at the end, I believe.
Okay. So you still get a DA of, sorry, you said?
I'm just gonna recheck the math quick,
sure.
because it's
Yeah.
it ends up boiling down to being negative 319.87 equals 2. I had it as a positive 500.31 dA,
Okay.
boiled down to its simplest form. So when I divided the negative by a positive, it gave me a negative answer.
Okay. Try again.
Yeah, still 0.64. Well, 639
For D?
for dA. Yes.
For DA, 0.60 something? No.
No.
So let me double check. Just gonna take my calculator here. So we have minus 4/5. MA 4/5, that one. Okay, cosine. That's right. I'm just gonna double check all of the numbers before I
Oh,
start the calculation.
Okay, I just saw my other mistake. I didn't put dA
Okay.
with the negative mu
Okay,
portion. Okay.
no problem. Times MA, which is 35. So do we have an answer of what's in front of dA? You should be getting something like 202. Now, mg is a force, so 202 newtons. dA, or if you want to keep it in kilograms meters per second squared, that's fine too. Maybe I'll just do it that way, kilograms meters per second squared. And everything on this side is equal to what? If you plug in your numbers. Should give you something like this, which means that dA is 1.07 meters, which is the answer that we get using the other method. In this particular problem, the other method may be a little bit more straightforward because you avoid having to worry about the initial zero references, but nevertheless, you still need to be able to do this part here.
A miss?
Yep,
I don't know if I missed it, but did we find I earlier?
I is given.
Oh, okay, okay.
So our next problem in the notes again. This next problem in our notes, we used this method to do the problem, but I'm going to use now method 2 to show you the other method. So it's the question. And in this case, we have our double pulley D has an inner hub and an inner pulley and outer pulley. The double pulley, the whole pulley has a mass moment of inertia of 150 feet pounds second squared. If the system is initially at rest, we're asked to find the velocity of A just before B hits the ground. So A is on the ground here. A starts to go up. B falls down. When B hits the ground, what is the velocity of A when B hits the ground? That's what we're being asked. Why is that there? Okay. PowerPoint's kind of acting up again. Anyway, we'll leave it there. So again, conservation of energy, but we're going to use the other method. Your choice, which one you want, which method you want to use. Nobody's going to tell you have to use one method versus the other. Whichever one you prefer. So we always start with our conservation of energy equation. In this mode, method 2 version, the change in energy is going to equal to the change in kinetic energy of all the things that are present, plus the change in gravitational potential energy, plus the change in spring potential energy if we have a spring. And all of these changes are going to equal to any work done by friction from initial to final position. So now we have to solve for this. We don't have a spring, so this is 0. And in this particular case, we don't have friction, so this is 0. I'm just going to do this. So delta K. Delta K in this case is the change in kinetic energy of mass A plus the change in kinetic energy of mass B plus the change in kinetic energy of pulley D. So we have to find these 3 changes. So the change in kinetic energy of mass A, kinetic energy final minus kinetic energy initial, which is 1/2 MAVA final squared minus 1/2 MAVA initial squared. Now we're told that the objects start from rest, so our initial kinetic energies are 0. So we just have 1/2 MAVAF squared. Change in kinetic energy of mass B, KB final minus KB initial is equal to 1/2 MBVB final square. All I'm doing is putting the definitions. MBVB initial squared. Again, we're told that they start from rest, so these are 0. So we just have 1/2 MBVB final squared. Change in kinetic energy of the pulley. K pulley final, K pulley initial. Now it's a pulley, it's rotating, so it's 1/2 I omega D final squared minus 1/2 I omega D initial squared. Starts from rest, so this is 0, this is 0. We have 1/2 I D, I guess they're both D's here, omega D final squared. So here we have VA, VB, omega D. We're being told to find, this is what we need to find to solve the problem. We don't know this, we don't know this. This is the actual known. We're actually being asked to find the velocity of A just before B strikes the ground. Now, these 3 quantities are related. How?
They have the same points of contact.
Not exactly. Close though.
Or like the same rim.
Okay. Some of them are going to be identical. Some are not going to be exactly identical. They're going to be related. So how? Which ones are identical?
B and D would be identical because it would be I'm assuming that D is the smaller circle, not the bigger circle. If it's the bigger
Mhm.
circle, it would be related to A. If it's a smaller circle,
D is
it
the
would-
entire thing. D is this and this. It's the hub and this, the whole contraption, let's say, is called D.
Okay. So we would have to solve using the radius of the smaller one.
Okay, so what would I
because
write?
they
Let's say.
obviously D constantly has the same I. Oh, hold on. Would we be using the VAB equals RAB omega AB formula again?
Yeah, so let's say VAF is equal to which R, which omega? So VAF is equal to V of the pulley outer, if you want to call it that.
So the radius would be the 5 radius.
So
For
the
this one?
5. Okay, so let's just call it R outer for now.
Okay.
And omega what?
Outer.
Well, is there an omega outer really?
Well, I mean, with the whole system would have the same omega.
Okay, and which omega is that?
Omega D.
Omega D. And our VBF is going to be equal to V of our pulley or V of our D. I'll call this D and keep it. I'll call this D out like we said. Not doubt, but D out. And this one here, VBF is equal to VD what?
EDN.
Yeah, inner. And so we'll have RD inner and
Then omega D.
omega D. And then omega D is just omega D. So these are all Fs, since these are the Fs, final versions. And we still have our omega DF. So in actual fact, it's easier perhaps in this particular case to find the omega F, write everything in terms of omegas, and then go back to this equation to solve for VAF. It's your choice, really, if you want to substitute in, rearrange the V's, but it's probably easiest to keep them as omegas. Omegas are common. It's the three are linked through the omegas. Do you see that? These problems, it's not so much the energy part that is going to be problematic. It's applying what we learned before because they're interrelated. The relationships here. You're going to need to apply these in order to solve for the unknowns. So in actual fact, I'm just going to write those, move those up higher. So here, oops, this is going to become 1/2 MA. Our VA, we're going to write it as RD out, omega DF. Why did I put a square for? Oh, yes, I know why I put a square for. Instead of doing the whole thing RD out, I'll just write DO so that we don't have to write the whole word here. 1/2 MB RD inner omega DF squared equals 1/2 ID omega DF squared. So everything's going to be in terms of omega DF squared. So these are our delta Ks. We add them all up. That's going to be the delta K that we're going to substitute into here. So this equation is our equation 1, 2, 3, 4. Oh, maybe I should keep this one in mind. 2. Oops. So what's the next thing that we have to do?
We expand the UG.
Yep. So we do the delta UGs for each one of them. So delta UG, I'm just going to take this again here. Oh, something froze. Do you guys see this little square that says slide 2 of 3? Or is it just on my screen?
Yeah, we can see that.
No, I see it.
Yeah, I don't know. Okay. Just annoying, I guess, than anything else. I'll probably have to close it and start it up again, but I'll just leave it there. Okay, so delta UG. Delta UG is going to be delta UG of A plus delta UG of B plus delta UG of D. So now delta UG of A. Definition is, if we write it this way, it's easier to write like this. MAG delta HA. So MAG, the change in height of mass A. Well, if we go back to the problem, we're told that mass A here climbs up and B hits the ground. So mass A climbs up and B hits the ground. So what is the displacement? What is the height change of mass A? When B hits the ground, mass A is where? Its height has changed by how much?
10 feet because the rope never changes length.
Okay, so 10 feet, positive or negative? Is it a positive change in height or a negative change in height?
If the reference point is the floor, then it would be positive.
Very good. So yes, we'll consider the floor to be our zero reference height. And so positive 10 feet. And actually, I'm just going to write this way. Let me just assign it a letter, capital H. So positive, capital H. Actually, I'll write it here so we have more space as well. Now, delta U GB. MB G delta HB. An analogy is going to be, therefore, what? What is its height change?
In this case, negative H.
That's right. So now we have that and delta UGD. What is the height change of the pulley?
There is none, so it would be considered 0.
That's right. Okay, so now we have this here. We actually have everything here, numerical values we have, etc. So if we plug in some numbers, what does that give us? We have the mass of A, we have the mass of B, we have G. Now, G is what in this case? It's the US system. So what is G equal to? You have to know this by heart.
32 foot-pounds.
Not foot-pounds.
Feet per second squared?
Yeah.
Okay.
Okay, so just like it's meters per second squared, it's going to be feet per second squared. So we have that G, we have our M. Oh, actually, guys, you don't even need G. Why? I just realized. Why don't you need G? What are you being given? Are you given the mass?
No, you're giving pounds, so G is already incorporated.
Yeah, you're actually being given the mg values. Okay, so in this case, you just take the actual numbers, even better. So you have your 2,000 pounds for B and 966 for A. Our H is 10 feet. So what does that give us? This one here is 2,000 pounds. Again, our H, but it's minus in this case.
In this case, the number should be negative, yes.
Oh, because we have the negative, this one, yeah.
Alrighty, so it'd be a negative 10,340.
Oh, you mean the total you gave me already?
Yeah.
I was looking for the individual, but okay.
Oh, sorry.
No, that's fine.
Well, it's timed, it's multiplied by 10 each, so it's just added 0 at the
Yeah,
end.
exactly. So now the thing with the American, let's say, pound, foot, or foot, pound, when you are, let's say, doing torque, in terms of torques or moments, it would always be, let's say, pound, foot, okay? But for energy, it's actually foot, pound. And it's, I don't know, strange that way, but it doesn't really matter. I wouldn't worry about that sort of thing. But let's give the final answer here. So we already have for Our answer, sorry, Ailish, you said was
10,340.
positive or negative?
Negative, sorry.
Okay. Okay. So now, next, what is our next step?
Solve for delta K and then add it to the delta UG to find the delta E.
But can we solve for delta K as yet? Meaning, do we have, what is that we're looking for? And where do we have to
In
find
this
it?
case, I think it would be omega. That would be the only real unknown.
Okay. And so what do we actually have to do? So like you said, we have our delta UG, we have our delta K. What's the next thing? Go back to our original equations. Equation 1, we have our delta K written out. We don't have all the, because we don't know this. We have our delta G, delta UG. So our next step, this thing is 0, this thing is 0. So quite simple. We substitute what we have into our equation. So equation 1. Oops. So I'm just going to bring the delta G over since we have it as a numerical value. Don't forget the minus sign because we brought it over. Delta K now. Take these things and we incorporate them. And now it's the minus delta UG. So minus. Okay, so if we plug in, well, before we plug in numbers, let's say, just factor out the omega d squares. Oops, I forgot the R here. So what value do we get in this bracket here? So what does this bracket give us? If you plug in your numbers, because we know M. Well, actually, this is where you're going to need your G, actually, because we don't know M. We're given mg. So your mass is in slugs. G is 32 feet per second squared. Mg is in pounds. So if you're looking for M is going to be your mg value divided by G. So your pounds value divided by 32. So if you put in your numbers, what do you get for omega df?
For omega, I got 2.2.
2.2.
Radians per second, I believe. Yeah.
Yeah, I got something more like 2.3, but okay, 2.2, 2.3
Well, I got
rads per second.
2.157.
Okay, when you plugged in all your values for here, what did you get?
It might just be rounding because I rounded way early on.
Okay, that's fine. So we have this, which means therefore that our final speed of block A, actually block B, say when it hits the ground. Oh no, we want block A's value when B hits the ground, sorry. Well, we have our RD out and our omega df. Actually, we should write this as feet. And so what do we get? And if we want velocity, well, we know it's also moving up.
Miss.
Mhm.
Just to know, does the radians disappear for any particular reason? Does it get like absorbed
Yeah.
by the feet?
Yeah, because it's the unitless unit that we've been saying.
All right.
Okay, so that's that problem. Next problem. Let's see. Mhm. Just debating which one to do. How- I think I'm going to leave the one that's in the notes because I believe it's also an assigned problem. If I'm not mistaken, let me see. Actually, I'll just do it to make it easier. Okay, next one then.